So today, Arnaud and myself will give you an introductory presentation on energy statistics, starting with the fundamentals and how we can build a national energy information systems. So what are the best practices, but we will also see how we ensure data quality. I will leave the floor to Arnaud that will start with the presentation, and then I will come back to you very soon. Thanks, Arnaud.
Thank you very much, Gianluca. Can you just confirm you can see my screen? Okay, perfect. So good morning, everyone. It's a real pleasure to start this first webinar and this course. I'm very happy to share our knowledge and also to learn from you more about the Ethiopia energy sector. So my name is Arnaud Rouget. I'm working in the World Energy Outlook team as an analyst for Africa and energy access. And so this team is mostly working on modeling and long-term scenario. But today, before looking at modeling and projection, we'll need to work on statistics. So some of you are professional energy statisticians with years of experience. So what we will discuss today might be obvious, but we will try as much as possible to bring to you our broader perspective as an organization working for nearly 50 years with many countries in the world. And we also feel like it's important that all of us share the same language and share the same common base of understanding on energy statistics. So today, our presentation will be threefold. I will start by presenting really the fundamentals of energy statistics. Then I will talk more about energy data collection process and its implication for a given country. And last, Gianluca will share with you best practices on how to validate and check energy data. So before we start talking, we wanted to hear from you and to do a very quick warm-up thanks to an online poll. So let me share a new screen. Okay, so you shall be able to see on my screen that we are inviting you to go to www.menti.com and to use the code 8965. So here we are asking you a first question. And this question is, what are the energy units that we use in an energy balance? So it can be financial units, like cubic meters, tons. It can be energy units, financial units, or I don't know. Okay, we have a first answer. I let you a few seconds to give your view on this question. And I see that some participants are answering in the chat. If you can please go to the menti.com tool so that everyone can see your answer and we can have a kind of classroom-like interaction. Okay, so to most of you, it's obvious. Sorry. Okay, to most of you, it's obvious that in an energy balance, we use energy units. Indeed, this is the case. I'm sorry, we're facing some technical issues. I will move to the next question. So another very quick warm-up question. What is a calorific value? And you have three options. So, okay, we have people very fast to answer. Calorific value is the quantity of energy contained in a unit of fuel, or is it the temperature at which a gas changes of phase? Or last, is it the monetary value or price of a fuel per unit of energy? Okay, so it looks like our questions were way too easy because all participants had the good answer, but at least it enabled us to start with this interactive poll. Okay, so I switch back to the presentation. Okay, so thank you very much for answering those questions. So it's good that those 2 points are clear to you. Well, let's start with discussing the basics, since energy data and statistics are really the foundation that give the ability to understand the entire energy system. So as we all know, energy plays a key role in our economies, in our societies, in our lives. So having reliable and high quality data and statistics has always been a concern to the statistical community. Still, several decades ago, quality was not as good as it is today, and there were sometimes some inconsistency between methodologies. All organizations were not using the exact same definition, the exact same scope. So there was a need for a common framework establishing some standard. And today, this framework exists, and it's the International Recommendation for Energy Statistics. And it really enables us to speak the same language. So this is approved by an international organization, and in the early years 2000, the IEA undertook an initiative to organize a group, Interstat, composed of various regional and international organizations, and to act as a secretariat of the International Recommendation for Energy Statistics, which is under the United Nations Statistics Department. So you can see a few organizations who are part of this committee. For Africa, AFREC is of it. And of course, the IEA has been working for a very long time with AFREC, with a very good partnership and very fruitful collaboration over the last years, and that is to continue. You also have another African organization, which is UEMOA in West Africa. And these IRES really provide comparability of production, transformation, and demand flows for all the energy products. And the main point is really to enable transparency and harmonization. So having a reliable and harmonized data is really key for analysis and decision making. And we really emphasize that all countries should refer to IRES for their statistics. So how can we structure energy data to get a picture of a given region or a given country and to understand better the energy system? So the key breakdown is between supply and demand. When we look at supply, we first consider production of energy. So it can be marketed production directly or from other sources. We also need to add the imports, withdraw the exports. We need to consider the energy for international bunkers, and here there are several statistical methodologies. We need to consider stock variation, and this gives a picture of the supply. Then we have to look at demand as well. And here, let's first focus on the consumption and transformation for the energy sector. So for example, if you take a refinery, its main activity is to transform energy products, taking primary energy products like crude oil, and to transform them into secondary energy products like gasoline or other end-use oil products. So these are transformation. But the energy sector also has its own consumption, and still in the example of the refinery, it will maybe use some oil or some gas for its own industrial process, like for the steam cracker to create heat, and energy will be consumed locally. So these are some first bricks of the demand side. And then, of course, we look at total final consumption, and here it can be broken down into subsectors. So we are regrouping them into industry, transport, residential, commercial, agriculture, and non-energy use. But of course, each and every of those subsectors are again broken down into much more categories. And between supply and demand, there are some statistical differences, because the data you will collect from data provider on the supply side will not exactly match the data you will collect from the demand side. This is normal to have a difference, but then you need to ensure that this difference is not too big. And statistical difference are really a key indicator and a very useful tool to check your data. So Gianluca will detail more on this. So this is how we can structure energy data, and this breakdown works at several levels. It can work to give the picture for a country, for aggregated regions, or even for the world. Then, in which unit shall we treat energy data? This is a question we shall ask ourselves before starting, because again, we all need to agree on a common language. And we know many units related to energy. We can speak in volumes like barrels, liters, cubic meters. We can speak in mass with kilograms, tons, pounds, other. And we can speak in energy units. So to have a unique language, we choose to express information in energy units. So the data we collect are usually in physical units, like 1 ton of wood, that's many barrels of oil, sorry. And we need to use a conversion factor, which is a calorific value. So a calorific value represents the heat that you obtain from 1 unit of fuel when you burn it. So it really gives you an indication of the quality of the fuel. The highest the calorific value of a fuel, the higher the energy it contains. And it's really useful, because if I propose you to choose between 1 cubic meter of wood, 1 liter of oil, and 1 ton of coal, you don't know what of these options makes the most energy. So you need calorific value to make the best selection. And well, calorific value are different between the fuels. This is obvious, but they can also be different for one fuel, because you have, for example, if we look at bituminous coal, you have different qualities. The one in South Africa has a way lower calorific value than the one in Morocco, and this really depends of the nature of the ground of the resource. So whenever you collect energy data, usually you will collect it in physical units, you need to collect the associated calorific value. And it's even a bit more complex, as actually there are 2 different calorific value, called the net calorific value and the gross calorific value. Why is that? Because when you burn a fuel, you have the energy of the fuel itself, which is useful heat and energy, but you also have water vapor. So the gross calorific value encompasses both, whereas the net calorific value just includes the useful energy. As a result, the gross calorific value is always higher than the net calorific value. So when a calorific value is reported, it's really important to ask yourself whether it's in gross or in net calorific value. And well, as soon as you have one, you can convert to the other, and you can use some standard ratio to make the calculation. For example, standard says that net calorific value of natural gas is 90% of the gross calorific value. So when a country needs to report its energy data, it will usually report unique data for the physical quantity, but also unique data for the calorific value. But if you have energy coming from different sources, you would need to calculate weighted averages. So let's take the example of a country that is producing natural gas from 2 different fields. So each field has a level of production. Field A, it's 4 billion cubic meters, and field B is 1 billion cubic meters, but the calorific value of each field is different because the nature of the chemical nature of the gas is different between those two fields. So what will be needed here is to report the 5 billion cubic meters produced, so this is the physical unit, but also to report the average calorific value. And here it needs to be reflected that the quality from field A is higher than the quality from field B, and calculation of a weighted average needs to be done. I won't enter into the math and the details here, but you have the generic formula is just calculating the weighted average to ensure that you report a unique number for the calorific value that reflects the weight of each field and its respective calorific value. So now we know that energy data will be reported in energy units. Let's see how to present all the energy data of a given territory. So at the IEA, we use energy balances. And it has an important, it's interesting because all flows and all energies are represented in a single table. So here you need to choose a unique unit. In the case of the IEA, we have chosen to work with kilotons of oil equivalent. You can choose something else, but you just need to specify it. And such table is structured in 2 ways. So the columns you can see are all the fuels and the energies, and you have a total column on the right. And the lines will take the structure we previously discussed. So you will see supply and demand. And as we said, demand will be also broken down by consumption of energy sector, transformation, and then the final consumption. So an energy balance is a very powerful tool because if you take the data of one country, you can include them all in a table, and you can very easily and very quickly read some key information like what is the first fuel in the energy mix in terms of supply? What is the first source to generate electricity in a country? Or which sector is consuming the most energy? Is it transport? Is it industry, etc.? But you can also calculate very more sort of sophisticated indicator that are very interesting, like what is the dependency on imports, and then what is the energy self-sufficiency. We'll have a dedicated session on energy balance because we can really do a lot of interesting analysis based on energy balance. Okay, so now we've discussed and we are clearer on the basics. Now we wanted to discuss more with you the process of collecting data in a given country. So here we will present some generalities. Everything might not apply to Ethiopia, but it comes from our experience of working with different countries. So if we consider the role and the importance of energy statistics, one might expect that basic energy information would be available in a reliable and timely way everywhere. As we all know, it's not that easy. And if we want to have a detailed and a reliable energy data, it's really helpful to have an entire ecosystem and a set of enabling conditions. So first, we need to have a collection system, and this relies on several pillars. A legal basis is really key, and it's the foundation with, for example, statistical laws and other national laws and regulation that would say, for example, that reporting energy data is mandatory. So this is the necessary foundation, but it's not sufficient. We also need to establish institutional arrangement to ensure that data collection, data compilation is efficient and is really shared amongst the different players of the ecosystem. Another pillar is to have proper reporting and dissemination mechanism. What do we mean by that? Is that you will need some well-structured and organized tools like questionnaire, like draft tables for dissemination. You need to have the contact identified in each entity from where you want to collect data. And you also need to have timelines and to have planning. It's always easier to collect data and to treat them if you know when those data will be published, and if you know what they will be used for. And then, well, you obviously need resources, but also you need to review the methodology, because there are some changes in the energy sector, as his honorable minister was highlighting. There are new trends we need to adapt to, and it's important to make sure that those changes are reflected in the way we work on the data statistics. Well, collecting energy statistics has a cost. We know it, of course, but maybe an interesting question is to wonder what would be the cost of not having those information, and maybe the consequences would be with higher cost than what we invest in collecting energy statistics. So it should really be identified as an investment, but then of course it's a trade-off and a fine balance to be found between the data you really need and the means you can allocate to collect them. But of course, cost is a challenge. There are other challenges, and new trends again can be one. For example, off-grid electricity are really ramping up, but it's not yet clear how to collect data from solar home systems that provide access to basic electricity services. So these kind of new trends and changes can be challenging for energy statistics. Then there are specificities per region. In the case of sub-Saharan Africa, traditional biomass has a big weight in the energy system, but as we all know, it's very difficult to collect reliable data from traditional biomass. We will have a specific webinar dedicated to this topic, because it's really a key topic and a challenge. Another challenge relates to the liberalization of energy markets. A few decades ago, markets were more monopolistic, so it was easy to have data provided by one company who would overview the entire its entire sector. Today, with more and more players, you need to aggregate data collection, and it can be longer, and it can be more difficult, and it can also come with confidentiality issues, and we'll say a word on that. And last, of course, you have challenges related to lack of resources, fast turnover in staff. So you need to reactivate and to build new contacts with the organization you are working with for data collection. Okay, so let's just have a look at the process of treating data and the data chain. So we identify 4 steps. You collect the data, you verify it, you process it, and then you can disseminate it. So if we look at an example, let's imagine a concrete energy action. Someone is producing energy, or a refinery is transforming it, or someone is using it. So this is the energy action. It will be collected, and what we call the primary data collection is something that you, for example, would do from the Central Bureau of Statistics or from the Ministry of Energy. You would collect, verify, and then you would transfer or report this data to secondary players, which are international organizations like the IEA or AFREC, who will aggregate all those data to be able to compare amongst regions. And from those aggregated data, you will be able to provide really analytical information and material to data users, who can be policymakers or civil society or businesses. So really, from the energy action happening in real world to what we do of the energy information, there is a key role, which is the one that you are having, and which is collecting and treating the data at the national level. Let's have a quick look at the players which are involved. Of course, the energy ministry is one of the key players, because it sets the policies for energy in the country. The statistics office is also an important entity, and usually there are relations and established frameworks between those two entities. But what we observe is that the ecosystem is way broader. There are many more players than just the Energy Ministry and the Statistics Office, and it's key to collaborate with all those entities. For example, Custom Office can provide information from trade that would help you get a comprehensive and a complete picture and understanding of some energy flows. If we take another example on biomass, we know that it's a very complex topic. It relates both to energy, but also to the environment, to forestry. So here it's really important to collaborate with all the entities which are relevant and which are working on this topic. So here we wanted to pause a second and to switch back to a short online poll, because we wanted to ask you to share with us and to tell us what are the entities you are working on and you are working with, and cooperating in your daily energy data work. So if you go again to the www.menti.com webpage, using the same code or just refreshing the page you have, here we are inviting you to provide us the names of the entities, departments, organization with whom you are working to do your data collection or your data verification, your data work. Okay, we are seeing the first answers. Okay, so the beauty of this world of cloud is that if several people answer the exact same answer, but with the same autograph, the world will appear bigger. So for example, Central Statistics Agency might be an organization many people work with, because I understand that in Ethiopia, they centralize all the data collection. So I guess that they are providing you with many information. So I assume many of you are working with the Central Statistics Agency. We can also see the electric utility, of course, which are collecting many data regarding the power sector. Entities working on climate change, of course, and this is a topic we will discuss a lot and work on. We all know that energy is central to climate change, and that energy-related CO2 emissions are really the bulk of global emissions. I see forestry. Maybe it's related to work on biomass, as we said. I see regional energy offices. So indeed, it's depending on each country organization, you can have data collection at the local level. So it can be like counties in the country, or it can be depending on your structure and your administrative organization. Okay, so Energy Ministry is really coming as a main entity. I don't close the poll if you want to answer, and for those who are still answering, but I'm moving back to the presentation. Thank you very much for your contributions. Okay, so thanks again for sharing with us this this picture of who are the players you work with. So I think, as we said, you as we observe for all the countries in the world, there are many stakeholders involved, and collaboration between all the stakeholders is key. One reason for that, and we'll enter more into the tools and the sources to get data, is that the first tool you can collect your statistics from are administrative sources. And before you start collecting new data, you should always ask yourself if this data already exists and if someone else has already collected and proceeded and verified those data. For example, at the energy, you might be interested, or at the Ministry of Petroleum Products, you might be interested in understanding the end use of oil, and you would like to have information on cars. And maybe this is a data that the Ministry of Transport has already collected. Other example, as we said, trade and Ministry of in charge of customs might have some interesting data. If you want, for example, to get an idea of the decentralized solar systems present in your country, maybe the custom would be able, thanks to custom codes, to give you an idea of how many solar panels were imported, and this would be valuable information for you. So administrative sources are a first tool to easily get data that already exists. But then you can also rely on surveys. So surveys are very, very useful and powerful. You need to ensure that your sample is correctly and cautiously made so that you can extrapolate and it's representative of what you want to get. But the beauty of surveys is that usually you always have surveys which are recurring and that already exist. And it's easy to add one question in a questionnaire of a few hundred questions. For example, if you want to learn more about how do households do some cook for preparing their meals, or what is their source of lighting, you could just put those questions in a demographic and health survey. Another source is metering and measuring. So you would get the exact data on an energy flow, for example. It's so it's very accurate. It's very interesting, but it's very costly, and it's really relevant for infrastructure or industrial customers or energy transformation process. Like if you have an LNG terminal, you would have such a meter and get the exact data of how many billion cubic meters were imported, for example. And last, you can do some estimation. So here we are not referring to modeling, as we will do in the future webinars, of doing projections and scenario. Here it's more about trying to do calculation and to estimate. For example, if in 2019 you you've just done a survey and you get some interesting data, maybe this can help you deduct some data for the previous years where you did not have this survey. So you can use a proxy and you would be able to recalculate and to fill gaps in historical data. Okay, a last point to discuss is about statistical confidentiality. So confidentiality should be taken seriously. It's necessary to prevent unlawful disclosure of confidential data, because of course for some data provider like private sector companies, there can be some concern about the fact that they would report to you some energy data, and disclosing their data could have some negative consequences for them. For example, if a private company is operating all the coal mines in the country, maybe it will be reluctant to reveal its production data because it can be strategic information for the company. Still, so confidentiality is something to have in mind. Still, it can also be an excuse for some players to refuse providing data, and your role is to get as much data as you can and reliable data to give a good picture of the energy status of your country. So solutions needs to be found to ensure that you can collect all the data you need. Here, we give a few examples, but really the main idea is to have an open dialogue between the government and the public entities who are collecting the data and the private sector companies who are providing them, because there are always solutions to be found. For example, the government who is collecting the data can keep it internally and do not publish it if it's confidential, but could only publish aggregated data. So there will be no disclosure of the very specific data that would be of concern of one company, for example. To return on experience from the IEA, we were working in Eastern Europe with an oil company that was taken over by an investor, and they claimed confidentiality. They did not work to release the energy data. Here, what the IEA did is that we worked with the authorities and we found a way to decouple financial data that remained confidential and were strategic to the private sector, and energy data that were released. Similarly, recently in the UK, we wanted to collect LNG terminals data. There were only 3 players, and they did not want to share data because if they do, you can easily deduct the market share of the 2 others if you know yours. So what we found as a solution was to ask them to report data of a longer time lag. So it's past data, and there is no challenge for them. So solutions can be always found, and if necessary, energy data collection can also be enforced by law, if that can help to make sure that you have the legal framework, as we said earlier, to collect all the data you need. So I stop here with those basics on energy statistics and energy data collection, and I give the floor to Gianluca, who will tell you more about and who will share good practices on how to validate data and how to do some checks.
Thank you very much, Arnaud. I just want to verify if everyone sees my screen. Perfect. So we've seen with Arnaud already the fundamental of energy statistics and a national energy information systems. And then we'll try now to see a bit more about how we validate and ensure the quality of data. But before doing that, let's recap a bit what Arnaud just said. So what are the recommendations of the best practices to establish a national energy information system? As Arnaud said, we need to put in place solid legal foundations. So the data collection agencies need to have the legal authority and a mandate to collect and disseminate data, but in some cases, they also need a law to enforce it. So to be sure that they can oblige data providers to submit the data. After that, there is a need also of establishing a network of institutions that are working on energy data collection. So this can be, of course, the members of the Central Statistical Agency in the case of Ethiopia, can be also other ministries besides the Energy Ministry, can be also the Forestry Commission, really important in Africa for the biomass, traditional biomass consumption, for example. So this is very important to put in place a cooperation mechanism and to work all together on the complete energy data set collection. It's also important, as Arnaud just said, to build procedures to deal with confidentiality issues. So in order to be able to make data provider more at ease to submit the data, but also to be able to disseminate this data. So Arnaud already speak about that. It's just a way of finding a balance of what can be disseminated and what not, and trying ways to show it the best practice way. Then there is a very important point now, that is establishing a data collection strategy. So once we know what data we need to collect, is the time to develop and design a strategy. So to allocate resources, both human and funds, so monetary, and also to not only to data collection for it, but also allocate these resources to improve data quality, also for historical data, and also to publish and disseminate better data with accessibility, so easier to be downloaded and used by data analysts, policymakers, and whoever else can benefit from good energy data. After that, there is a really important concept, is providing metadata. This means that you provide additional information to the data that makes you able to understand what the data is saying. So beside the value itself of a data point, the metadata tells you what this data point means. It can tell you if the data is estimated, it can tell you the definition of this energy product or flow. So metadata are really important to make data users able to understand what they are reading from the data. But now let's try to focus a bit more on the data collection strategy. So how do we start a data collection strategy in energy data? First of all, we need to identify our data needs. We can have national data needs from our policymakers or other institution. We have regional data needs. The example for Africa is the Agenda 2063, and international data needs or requirements. For example, the Sustainable Development Goals reporting of indicators. Once we have identified these data needs, we can try to map what we already collect and how we cover these data needs. So we can see, as Arnaud showed from administrative data, what National Statistical Office and other ministry are already collecting, or other public and private actors or international agencies are already collecting in terms of this data, and how these satisfy the data requirements that we identified in the first step. So comparing these two, the data we need and the data we already have, we identify our data gaps. That means what data we really need to collect. This doesn't mean only a specific data point like natural gas production or transformation. This also means the proper level of requirement. There can be frequency. For example, we have annual data, but we need monthly data. So we need to start collecting data at a higher frequency, or we need a higher level of details. For example, we need a breakdown of energy consumption in different sectors that is higher than what we currently have. After we identify these data gaps and what we need to collect more, we can establish a strategy to collect the required data. And this strategy should be included in the national data collection strategy that normally is managed by the National Statistical Office. So what does this include, the national strategy? This is just 2 bullet points, but includes much more than that. Is the allocation of resources, so estimating how much staff, people, how much money for example, data collection and service, and how much new IT tools like computers, softwares, we need to put in place this new data collection. And what data collection or data includes? The data work includes not only the collection, but the verification of data. As you will see, we need to ensure that the data are of high quality, data calculation or processing. So we need to be sure that we put this data in a format that is useful. For example, the calculation of energy balances or the estimation of CO2 emissions due to energy consumption. And then disseminate this data that needs to be done in a useful format. So now said that, I can tell you that there are resources to understand better the topics of energy statistics. Arnaud already mentioned the International Recommendation for Energy Statistics, which gives clear definitions of energy products and flows. But there is also the IEA and Eurostat Energy Statistics Manual that is downloadable for free and gives a comprehensive understanding of what energy statistics are, how you report energy balances, what are calorific values, and go in depth on some of the main fuels and topics. We also have other manuals. The IEA, for example, developed a manual to calculate energy efficiency indicators. That is really interesting because there is a need of coupling energy data with other activity data in order to calculate these indicators. And this manual gives you best practices in order to establish a national energy efficiency tracking system. So to put in place indicators that will be useful to collect the required data. But say that, let's start now with ensuring the data quality. But what is the data quality? I think we could describe data quality with 5 main characteristics. The first one is relevance. That means that the statistics we collect and we disseminate needs to be useful to the users. So they need to meet their requirements for analysis, for policy making, for whatever else they're doing. For example, modeling and projections. Data need to be accurate and reliable. So it means that they need to illustrate a real portrait of reality. They need to be as close as possible to reality. They have to be timely and punctual. This means that we want to collect data that is as recent as possible. So if you're speaking, for example, about annual data now in 2020, we would like to see data of 2018 or 2019, not data of 2015. Of course, we're interested also in 2015, but we want also to know what happened in the latest period possible. And also they need to be punctual. This means that they need to be published and released when agreed, and every year or every month in terms of monthly data at the same time. So data users can rely on this data when they plan their work. They need to be current and comparable. That means that statistics need to be consistent internally. So if a data point is related to another data point, this needs to be the case. If not, there are some problems with the data. And comparable. This means that we need to be able to compare data between regions, countries, between different tables. And this, as Arnaud said at the beginning of the presentation, can be done by using harmonized definitions as the one provided by the IRES, the International Recommendations for Energy Statistics. And last but not least is the accessibility and clarity of the data. This means the data needs to be clear and easy to understand, both in the format they are, but also on the, for example, the files that can be downloaded, the way they can be downloaded, the easiness to find the data in a specific website, for example, but also they need to be together with metadata, so supporting explanation of what the data means, as we have seen before, and guidance. There are some guidelines for data quality internationally recognized. There is one interesting from the United Nations that wrote the Fundamental Principles of Energy Official Statistics, for example. It is an interesting document to understand what data quality is and how it can be ensured. As well, there are some documents from the European Union and other specific documents for Africa. But let's see now how we really do this data check and ensure that the quality is there for energy data. First of all, we speak about internal consistency. This means that if we have a data field that is supposed to be the sum, for example, of two others, we need to ensure that it is the case, so that there is no errors on, for example, the data processing we have done. For example, if you have the total primary energy supply, that is the total energy available to the country, is this really the sum of production, trades, bunkers, consumption, stock changes, etc.? Is it the case, or we have a problem in our processing of data? Does the breakdowns of, for example, demand sectors match the total? So all the subsector consumption in industry is equal to the total industry consumption we are showing in our energy data tables. Are the stock changes calculated correctly? This is an important topic because stock changes can go in one direction or in the others, and are represented only by one flow. So depending on the sign they have in front, minus or plus, they represent either a stock built or a stock drawn. Because if our stock of a specific products are increasing during 1 year, it means that we have less available energy of this product in the country. Instead, if the stocks is decreasing, it means that we have higher amount of this product available in the country, because we release some of this product from the stocks. And this is important when reporting the signs of stock changes. Is the data complete? That's, of course, are we covering all the sectors for consumption, all the production for all the energy products, etc., etc.? Is another important question we have to ask ourselves. And also, when we look at trends, for example, the decrease in one specific fuel, is it going together with the increase of another one? For example, we have seen in energy history a lot of energy revolution. For example, from the consumption of coal, countries globally moved to consuming more oil. Then from oil, they moved to consume a bit more gas. This is not the case for all countries, but in general, we see this kind of energy switch. But the energy consumption in absolute terms is not directly decreasing. It's just that we are using other fuels, but also we are increasing our efficiency. So there is some decreasing factors as well. Is the story my data are telling making sense? So what the data says is logical and is linked to reality and to the news, to what is happening now. For example, now we are in the pandemic situation. Is the data in collecting now for monthly, for example, statistics showing a big decrease because we are expecting from the lockdowns that people are consuming less energy. So this is an example. It's also a very important practice to be sure you analyze how you process the data and what are the validation processes. So for example, if you have a data processing, that is maybe some calculation, extracting different data points and putting them together with some calculation or algorithm, this can always bring to a mistake. Can be one item that is dropped or counted double. There can be a loss of one of the part of the data sets. So we can have this calculation leading to a mistake in some cases. So we need to put in place verification procedures that, for example, aim at comparing the data after the processing and before the processing and make sure that there has not been any unwanted change. So this verification is just comparing the data and telling us if there has been an error during my calculations. After that, let's go back to the statistical difference that Arnaud already showed really well what it represents. As we said, statistical difference is the difference between the energy supply in a country, so how much is available to the internal national market in terms of energy, and the demand, so how much is consumed in the market. So this difference, as Arnaud explained really well, comes because there are challenges on data collection, and many times when we collect data on supply, we are collecting this data from different actors, for example, to our own energy producers. And when we collect it from demand, we are collecting this data from other actors, like, for example, households or industry actors. And also sometimes there are differences in definitions, in coverage of survey samples. So this can bring to a statistical difference. So we'll have a difference of the supply and the demand that in theory shouldn't exist because energy doesn't create or disappear, but it comes because of the statistical process of collecting and disseminating, calculating energy data. So we have seen that it's normal having it, but of course we need to check it and verify how big the statistical difference is. A good way to do that is calculating the ratio of the statistical difference out of the supply. So if we divide our statistical difference by the total primary energy supplies, we will have a ratio and can give us an idea of the size of the statistical difference. We normally say that if this statistical difference is higher than 5%, this could be a problem with the data, either on the supply or in the demand side. But also, if we have a statistical difference that is 0, it could be suspicious because, as we have seen, it's practically and theoretically impossible to get supply and demand equal from data collection. So a number 0 in the statistical difference is 100% of the time artificial. That means that there are some flows on the demand or the supply that has been calculated as a residual. For example, if we have more supply than the demand we have collected, we are assigning to some energy consumption sector this difference in supply and demand. So this, of course, is not the best practice. It sometimes can be done, but of course, if it is done, it's very good that this is recorded and metadata are provided to explain that this specific flow has been calculated or estimated as a residual because no additional or real information were available at the time of this data publication. But what we can do when we flag a big statistical difference, where the problems can come from. So the problem can come from supply and demand, or demand, all the different flows. We have to check, of course, that both of these supply and demand are complete. So we are not losing any subsector or any subflow. Like, are we taking into account all imports and all exports in our supply calculation? Are we taking into account all industry sectors, or we are forgetting to collect the data from a sector that is important for this energy product? Then there is also double counting. Sometimes there are data that are collected twice or reported twice because data processing went wrong. So when we have this statistical difference, it's really important to try to find out why. And often is easy to spot the problem because we know where are the data that are official and collected and we are confident with, and we know what are the data that we are less confident with, so we can try to find out, doing also additional checks that we'll see later, find out which is the data point that may be causing the problem or the data that is missing. We have to review the definitions and methods used for both supply and demand data sources, and of course, check that the calorific values used for both supply and demand are comparable and using the same definitions for the products that are available in the countries. Then also need to check if there are new trends that are not taken into account in my statistics. For example, renewables are growing up really fast and maybe we are losing this trend, or in case of Africa, there is a lot of off-grid and also new grid connections, and so new production also from mini grids plants. Is this taking into account in my statistic both in supply and demand? So these are some of the questions we can try to verify if we have a big statistical difference. But let's now see a bit an example on electricity. For electricity, we can check, of course, the efficiency of electricity production that you can see later, but two other interesting parts of the electricity value chain that are the own use and the losses in transmission and distribution. As regards own use, the own use represent the electricity that is consumed by a power plant for its own functioning. So for example, for lighting the premises, for the functioning of some electronic equipments or electric equipments like transformers or other kind of power electronics that are needed to put the electricity later in the grid. This value is normally expected to not vary very much year on year and is normally around 3%. As you can see from this graph, African own use in average from the data the IEA collected from the African countries is around 4% today, and the non-OECD average is around 6%. So we see that own use is not very different across countries. It can be different across different kind of plants and countries, of course, but it doesn't vary very much. So if we see a own use of 15%, 10%, this can be a mistake somewhere, either in the production or in the own use reported by the plant itself. Then there is transmission and distribution losses. If we calculate them as a ratio of total electricity consumption at the end users, they should technically be below 10%. However, since in many countries the grid is badly maintained and there are a lot of thefts directly from the distribution grid, so people that are just taking the electricity without paying for it, so this is not taken into account in the demand statistic, unfortunately, so many times, losses can be as high as we have measured in some countries as 30%. Let's see how is the situation around the world. We can see that non-OECD countries, for example, the green line has been decreasing quite quickly from the 2000, where we had like around 17% of losses as out of consumption. And today we have around 11, 12%. We can see in OECD countries where the grid is maintained properly and is new, and also there are less or virtually no thefts, even if there are. We have seen some cases as in Paris, actually. The losses out of consumption are relatively low, so they're around 7%. In Africa today, 2017, so the latest available data when we are producing this presentation, we're around 17%, so a bit higher because of probably the presence of thefts in many countries and also of the maintenance of the grid that was poorer than needed, so led to higher losses in the transmission and distribution of electricity. After that, we can speak about calorific values. Arnaud already said a lot, so I don't want to spend too much time, but we know that calorific values are essential to build energy balances, so to convert from physical to energy units. They are specific for each energy product, and for a type of product, we have an expected range of calorific values. For example, if we take the example of coal, that is maybe not really relevant for Ethiopia, but is interesting. If we take, for example, the sub-bituminous coal, as you can see in the table, we will expect calorific values around 16 and 24 megajoules per kilo. If we see a value that is much higher, and we are reporting this as sub-bituminous coal, we can ask some question and see if is the calorific value correct, or if this product is reported in the correct category, or this may be another type of coal. It's important also to know that calorific values, as I already said, varies between region, because the quality of the products extracted in different mines or fields is different, and also varies inside the country in different sectors of consumption. This is because often the mix of the products that goes to a specific industries may be different than the mix of the products inside the same category that is going on another consumption category. So it's important to track as best as possible the calorific values, and to ensure also that these are correct by looking at expected ranges. Now we can speak about growth rates. This is a trend check. This means that we are going to check the variation of energy data, so for example, consumption or production across a period. Namely, the growth rate is trying to understand the difference between the value, for example, of production this year compared with last year. This will give us an idea of if there is a big increase on the flow. And if it's the case, for example, if we see a production increase of 10% for natural gas in a country, we need to be sure that this 10% increase is related, for example, to the opening of a new gas field. If it is not the case, this could be a mistake in data reporting or collection. So it is important always to verify the trends and the growth rates, and try to spot possible mistakes, or validate that this growth is in line with expectation. For example, when we deal with monthly data, seasonality is really strong, because in warmer months, we need, for example, more electricity for air conditioning, or in colder months, we need more energy in general for space heating. So growth rates checks for monthly data is maybe less relevant, but can be used for checking the difference in the rate with the previous year in the same month, for example, as you can see from this graph on natural gas consumption. What is useful for? This is very useful for consumption, this kind of check, and production. However, for example, flows like stocks changes and trades is less relevant, because these two latest flows are keen to have an higher volatility. So it's normal to see a big change in stocks that can go from negative to positive, as well as for trades, you can be a net importer this year and become a net exporter next year, depending on different energy market conditions. Seeing that, now we can see a very related data verification, that is the break in time series. This can be spotted actually looking at the growth rates that you have just seen. As you can see in the graphs, you can see, for example, this big increase in biofuels and waste production in a country in the year 2000. And this can tell us, should make us, ask some question. Why is this increasing? Is there real or not? Sometimes this happens because there's a change in methodology, sometimes an improvement in reporting. For example, new data has been received for historics, so we are revising the data that we had in the past with better data. But this, since we often don't have the whole time series going back to older years, can create this break. So we can have from one year to the other a big jump. Very important to do is, if it is not possible to update the series with historical data to match the new methodology or the new definition that is more correct, what we need to do is either estimate it, if it's possible and easy, but in any case, we need to report it in metadata and documentation. For example, at the IEA, we will use country notes that goes together with our data publication that tells and explain why there are these kind of breaks. For example, we can say that for Ethiopia, this is just an example, we received new biomass data back to 2000, and so there will be a break in the time series between 1999 and 2000. So our data users will know that this sudden spike is not a representation of reality, but it's just a change in methodology, so it can adapt the data used accordingly. So again, the importance of reporting metadata and information about the data itself. So I think this we have already seen. Another data verification is verifying that the data is coherent. So is the data trends matching our expectation based on what is happening now? For example, the maintenance of a specific power plant, specific weather disruption, seasonality, so winter and summer, change in policies, etc. And certain of these trends and patterns are specific to certain specific fuels. I think really relevant for Ethiopia is hydroelectricity. So we know that a year where rainfall is very high will be a year of very high hydroelectricity production. So we'll see an increase of hydroelectricity production. Conversely, a very dry year with low rainfall will see lower hydroelectricity production in my country. An example I put here is about electricity production in sub-Saharan Africa and the access to electricity. We know that more people are getting access to electricity, namely from 2000 we are in sub-Saharan Africa about 25% of people only had access to electricity, and nowadays around 45, sorry. So we are expecting that since more people are getting more access to electricity and also population is increasing, we are expecting an increase of electricity production and supply. And this is the case, for example. But we have also to pay attention that there are different factors affecting a flow. So for example, we could have seen in a different scenario that electricity production was flat even if access to electricity was increasing. This can be also real in the case, for example, energy efficiency in electricity consumption is stronger and faster than new access to electricity or new demand. So we need also to be careful when we analyze this kind of trends. Then we need to be sure that data that are related are matched, even if they are collected from different sources. An example is I collect sales of a specific fuels to a power plant, and then from the power plant, I collect the use of fuels for electricity production. These are data that are related, so we need to be sure that these data are making sense when compared. And also the relationship between different variables need to be satisfied. This is an example about efficiency, so input and output to electricity production. For example, if we see an increase of the use of a specific fuels to produce electricity, we need to see also an increase of the electricity output. This is an example of gas power plants in Sub-Saharan Africa. And in the graph, we can see both the electricity production from natural gas and the natural gas used for production of electricity. We see that both are increasing. We also see that in 2009, there was a small decrease of natural gas use, followed also by a small decrease of electricity production, so we are okay. But then we could ask ourselves why they are diverging and decoupling. This is actually normal. The input is increasing at a slower pace than production. This is because energy efficiency of electricity production using natural gas in Sub-Saharan Africa increased from 30% in 2000 to 40% in 2017. So this is the main reason why we have this decoupling. Because as I said before, there are different factors that can affect the relations between two data variables. But it's always important to verify that this makes sense. Now I would like to go back again as well to the menti.com. So please, I can kindly ask you to connect again to menti.com or go to the same page you were before. And I will share the screen. Oh. One second, let you the time to connect. Okay. Oh. Here we are. Sorry for the time. Can you see my slide? Oh. So this is already an answer. So what is the question is how you can verify that the fuel that is consumed for electricity production and the electricity produced by a thermal plant. There are three possibilities. One is you have to analyze the trend of production in the past years, depending on the different technology, and see if the trend is satisfied, is going the same direction as before. Either you compare the ratio between output and input, and you verify that this is falling within expected efficiency for the technologies. And latest is you compare the levels of production for this technology with similar and neighboring countries. I'll let you the time to answer. Okay, we have now 6 respondents as well. Everyone is saying the same thing. Let's see if someone else has another opinion. But in any case, this is the correct answer. As we have seen, trends are important, but the relations between input and output for power plants is very, very important. So if we see that the efficiency 1 year from the other from a specific fuel or technology changed drastically, this could be a mistake in reporting either the inputs used for the electricity production or the electricity produced. Of course, also trends are useful. So if the efficiency is correct, if we have like an efficiency that makes sense for us, we can also verify the trend and see if there is a big spike in production from a specific fuel in the country, and then verify if this is confirmed by reality. For example, a new power plant opening or a power plant that declared that this year is producing with a higher log factors, so producing more electricity during the year. Thank you very much for the answers. Now, I think I had prepared another question. I'll try. Oh, yes, this is about efficiencies as well, but it's more about charcoal production and the efficiency of a traditional earth kiln. So the charcoal kiln or ovens used in the countryside traditionally. So not industrial or high efficiency one. You think the efficiency is around 80%. So you need 2.5 kilos of food for 1 kilo of charcoal. Is around 40%. So you need 5 kilos of food for 1 kilo of charcoal, or around 20%. So for every kilo of charcoal produced, you will need 10 kilos of food. This is because to use this mass conversion from the energy efficiency, I use the assumption that charcoal calorific values is double wood calorific values. That is the case in average. We will see that also in a webinar we'll have on biomass. So I've seen that many people answer, and there is different opinion, more or less of the same amount of people are saying that is around 40% or around 20%. The answer could be for me that the lowest efficiency is 20% for earth kiln. So a badly done, or not badly, just a typical and traditional earth kiln that is just a hole on the ground where you put wood, you cover it, and you let like the chemical reaction happen, is 20%. But there are some improved kilns that can arrive, of course, to 40%. But this is not the case for traditional earth kiln. And we can go also more than 40% when we produce charcoal industrially with some more efficient production plants. So thank you very much for this answer, but we'll see all these topics more in detail for charcoal and biomass on the webinar number 6, if I'm correct, later in July. So now I try to go back to my slides. Oh. Yes, it's here. Can you see my slides again? Perfect. So we had the questions about transformation efficiency. Let's now go to see on the slides what is transformation efficiency, how do we calculate it, and how we check that there are no problems with the data. So transformation efficiency is the ratio between the useful output, so the net energy produced, that can be electricity, can be oil products if you're speaking about a refinery, divided by the input. So how much energy was used in the to produce this output. In the example of a power plant, we can have two different fuel inputs. For example, a power plant that is burning both coal and biomass. And then we have the electricity output. How do we calculate? We divide the electricity output by the sum of the inputs, A plus B. And all this data needs to be in the same and energy units. So they have also to be both based on net or gross. In the case of electricity, there is no net or gross because it's not a combustible product, but in general, this is the definition. We need to use the same energy data when we calculate this ratio of efficiency. So how do we then check that this is correct? First of all, efficiency cannot be higher than 100% because energy cannot be produced from nothing. So if there is something getting in, we cannot get out more. This will be amazing, but unfortunately, permit us to do that. So below 100%, but also within certain ranges, depending on technologies and type of fuels and type of transformation. And also depending on for the same technology, depending on the state of the technology. Is this a new power plant, an old power plant? What is exactly the technologies involved? What is also the utilization? Is this power plant used at the most efficient way, so with a good load factor, or is used very erratically, like ramping up and down very quickly, that this reduce a bit the efficiency. So we need to take into account different things, but in general, efficiency need to be within specific ranges. These are also the checks we do in the IEA. And when we speak about that, we are not speaking only about electricity, but also about all the other transformations that can happen. As you can see, for electricity only plants, so where we produce only electricity, we can have between 10, 40%, and even more for some specific plants, but normally in the average in the countries, 40% is already a high value. But you have a plant if produce both heat and electricity, so combined heat and power plants, CHP, we can have much higher efficiency because of course we have also heat as output, we don't have only electricity. So there are less losses. And this is important when we verify our country efficiency. If you have a refinery in the country, we'll also verify that the efficiency is in their expected ranges, as well as for all the other transformation. And for charcoal, we can see that efficiency can range from 20 for the less efficient earth kilns, obviously in the question, to 70% for the most efficient kilns that are more industrial side, like with more developed like equipment, let's say. Now, I wanted to speak quickly about product classification. So when we collect data, for example, from trades, we collect them with a code associated to them. And this code comes from a classification system. Normally, worldwide, almost 98% of all traded goods are classified in the harmonized system, so HS, in order to make sure that we recognize the same product when it's going in and out of a country. The problem is that for energy, we also use other classification systems like the SIEC or the Standard International Energy Product Classification. And we can have also other classification when we take or collect data from other sources, like for example, the Central Product Classification. What is the problem? The problem is that sometimes fuels can have different names. The codes are of course different, as you see, they are not the same codes under different classification, but the names used for the specific product can be different. And also the same category, so the same name can also represent a different kind of product or a different defined product. So it's important to look at the definition, as we say, so metadata, definition of each data point, etc. It's really important to understand what you are using. For example, biodiesel in the harmonized system categorization can include up to 70% of fossil oil, fossil diesel, while in the SIEC, this is not the case. So it's a much different kind of reporting that is done there. And we need to be careful. After that, I wanted to speak about mirroring checks. These are mainly checks that can be done with data that are bilateral, so that they have a component that is the same on two different sites. A very a good example is trade. So when I sell a certain product to another country, this country is buying the same amount of products. So these two products or two flows of imports and exports should represent the same amount. How do we ensure that this is the case? We need to check and verify both reporting. In this example graph, we see in blue the imports of country A from, no, the exports, sorry, from country A to country B, reported by the exporting countries. While in the red line, we see this same exports, but reporting by the importing countries, so country B. We've seen that after a while in 2012, there start to be a big discrepancy, and this should not be the case because this electricity that leave one country and enter the other should be reported the same, but sometimes can happen for different reasons. And of course, when possible, this will need to be checked, above all on international energy statistics for organizations like the IEA or Africa, but also at the national level. It's good if you have a friend neighboring country with which you can compare your energy balances or energy statistics. Where this can come from different definitions. Timing, for example, one country is counting the annual trades at the specific dates, while the other is counting on a different date. One country might be calculating the imports based on different data sources than what you're doing, etc., etc. So it's important to check and maybe spot the difference and find out why they're there. The IEA can, of course, help to find neighboring countries' statistical offices or contacts for doing this kind of cooperation. And this program is all also about that, because now we're working only with Ethiopia, but we'll try to create a community where you can also share your practice and data and modeling problems with other countries that are benefiting from this program. Another check that we can do is verifying the coherence of my energy data with additional data that can be socioeconomic data, for example, GDP or population. So for example, we see a change in gross domestic product or in GDP. Is this affecting also energy consumption? This is most of the time the case. If there is a big decrease in the value added of the industry, that means that this industry, the manufacturing in particular, is producing less. So it's consuming less energy for its production. And as you can see from this example, in 2009, during the Great Recession, we have seen a big decrease in GDP in the IEA countries that was followed also by a big decrease in energy demand in the same year. Then we need and can and should, when possible, verify coherence with monthly and quarterly data. So for example, does the aggregated sum of monthly data adding up to the annual data we are reporting? Is this the case? This is very helpful also to be able to double check my data sources, but also maybe to correct some monthly data, because the annual consolidated data sometimes are of a better quality because they are collected more recently compared to the monthly data, which are collected on a more timely basis. So definitions and resources allocated are lower because of time constraints. Said that, all the verification, etc., what can we do when we have a missing data that we want to estimate? First principle is always better to collect and observe real data, but sometimes, unfortunately, it's not possible. And this represents a small proportion of my energy balance. It is okay to estimate, but we need to follow some specific practices. First of all, this should be short-term solution. We shouldn't be estimating a data point for like 20 years, for example. This is okay if you do it for 5 years, but then we should try to establish a data collection for this energy field. The strategy you will implement to estimate depends on the type of missing data, its importance, etc. And of course, every time we estimate, we should clearly mark this in metadata, in nodes that goes together with data, so people know that this is not coming from mere observation, but is estimated data. In general, we can ask the following question. As we have seen before, is someone else already collecting this data or data that are related? So I can just use this data instead of starting a new estimation. Also, I should ask myself, how important is this data that is missing? So I will be able to know how much resources I can put into the estimations. Also, I can check if this data can be estimated easily from other data that I already have. For example, if I'm missing input to electricity production 1 year for a specific fuel, I could try to estimate it by using the same efficiency as the year before. But of course, this cannot last in time. It can be a quick fix solution for 1 year, should be clearly marked, and we should address the problem on the data collection side. We can ask also, is there a seasonal or historical trend that I can use? And also, is this trend different in my period than other period? For example, this year is colder or is warmer than the previous year. So the demand for air conditioning or space heating can be different from previous years. Can I use other market trends to estimate this, etc., etc.? So these are the questions that we can ask ourselves. But mainly remember that it's better to collect the data. This should not be a long-term solution, and we should clearly mark that this is estimated. To finish, I would like to see what the IEA does for data validation. So after we receive the data from countries, like for example, Ethiopia send us data tables, we receive them, we process them. So what do? We do some checks for validating the quality as the one we have seen today. And also we do some processing. So we try to put together the data in other formats to create energy balances, to create other indicators. We also do time series check. So we check the data of the latest year that we received with the other years, as we have seen many time series check, like the breaks, like the growth rates, the trends, etc., can be also checked. And then if we find any possible problems, we communicate again with the data provider and try together to fix the data issue if it is the case. After that, when we freeze the database, we'll have further experts and analysts that will be checking the validity and quality of our data and provide further feedback for further data improvement. And finally, we'll publish the data for the external public in the form of databases, reports, and other publications. I hope you enjoyed the presentation, and thank you very much for having listened to us. We have been, I think, a bit long, but we had a lot to say today, and also the opening remarks at the beginning is really important. But please, if you have any question, don't hesitate. I will ask maybe Arnaud if you have read any questions through the question and answer. I see there is no question for the moment, but if you have, you can either write them in the question and answer log or send us an email later on so we can take the time to answer you directly if at the moment you don't have a clear question.
We will send you per email the presentation we just displayed. So if you have questions coming while looking again at the presentation, feel free to send per email.
Perfect. So I think that we can wait 1 minute more, but there is no question. As Arnaud said, we'll send this presentation and then we'll try also to put together recordings when possible and share it later on the program. I would like to thank you all for participating today. I hope you enjoyed. It was a bit long, but I think we said an interesting thing. And I hope we'll have the opportunity for next time to interact more after these webinars, to come to Ethiopia and to work together side by side, because I think this is the best way to work. But I think also this is already something good. So just to remind you, next week we'll have 2 webinars, one the 1st of July and the other the 2nd of July. And we'll continue to speak about energy statistics. We divided this webinar in 2 because it will be a bit shorter and it will be easier, I think, to follow during 1 hour or 1 hour and a half instead of 2 hours. So we'll speak about energy statistics for each of the different energy products next week. And then on the 2nd of July, we'll start looking at how we construct energy balances. Thank you very much for the time and the attention. And as Arnaud said, we'll shortly send you this presentation and an email with the next webinars and steps. Thank you. Bye-bye.
Thank you very much to all. Have a nice afternoon.